In this module, you will learn about locus and theorems related to it. Take a look at the plane. There are infinite points on it. Consider any arbitrary point in the plane and name it as O. Now, place at O a drawing pin tied to a strong thread. Label the other end of the thread as P. Let the string be of fixed length, say 5 centimeters. On moving point P around point O, we obtain a circle. A fixed point O is called the center, and the fixed distance OP is equal to 5 centimeters is called the radius of the circle. The path traced out by point P that satisfies the given condition is known as the locus of point P. Thus, the locus of a point under certain conditions is a geometrical figure, every point of which satisfies the given conditions. In other words, a locus is a set of points satisfying a given condition or conditions. Locus is a Latin word, which means location or place. The plural of locus is loci. Let us see some examples now. The locus of the tip of an oscillating simple pendulum is an arc with radius equal to the length of the pendulum. The locus of a point equidistant from two parallel lines is also a line parallel to the given line and passing midway between them. There are two important things to be noted here. Firstly, every point belongs to a given locus, satisfies the given condition or conditions. Conversely, every point satisfying the given condition or conditions belongs to the locus. Now, let's learn some theorems on loci. The first theorem states that the locus of a point equidistant from two given points is the perpendicular bisector of the line segment joining them. We are given 2 points in a plane. Let's name them as A and B. Let P be another point in the same plane such that PA is equal to PP. We have to prove that the locus of point P is the perpendicular bisector of line segment AB. In other words, point P lies on the perpendicular bisector of AB. We begin by locating the midpoint M of AB. Now, let's prove this theorem. Consider the case when point P coincides with M. Then, AP is equal to PB, since M is the midpoint of AB. This means P lies on the perpendicular bisector of AB. The second case is when P doesn't coincide with M. If P does not coincide with M, then draw PA and PB. In this case, let's suppose that point P lies on a line, say L. Now, we need to prove that PM is perpendicular on AB. In triangles AMP and BMP, AM is equal to MB, since M is the midpoint of AB. PA is equal to PB, which is given to us, and MP is the side common to both the triangles. This shows that the corresponding three sides of the two triangles are equal. So, by the SSS congruence property, triangle AMP is congruent to triangle BMP. Therefore, by corresponding parts of congruent triangles, angle AMP and angle BMP are equal. As angles AMP and BMP form a linear pair, each measures 90 degrees. This implies that PM is perpendicular to AB. Since M is the midpoint of AB, PM is the perpendicular bisector of AB. However, PM is the same as line L. Hence P is a point on L. The converse of the theorem states that every point on the perpendicular bisector of the line segment joining two points is equidistant from them. Let's prove the converse of the perpendicular bisector theorem. Let A and B be two given points. Let L be the perpendicular bisector of AB and M be the midpoint of AB. Let Q be a point on the perpendicular bisector of AB, that is L. Now, we need to prove that AQ is equal to BQ. Join A and Q and B and Q. If Q coincides with M, then AQ is equal to QB, since AM is equal to MB. This shows that point Q is equidistant from A and B. If Q does not coincide with M, then in triangles AMQ and BMQ, AM is equal to BM, since M is the midpoint of AB. Also, we have the common side MQ. It is given that L is the perpendicular bisector of AB. It implies that angle AMQ is equal to angle BMQ is equal to 90 degrees. Therefore, by SAS congruency, triangle AMQ is congruent to triangle BMQ. It implies that AQ is equal to BQ. This proves the converse of the theorem. Let's now see the angular bisector theorem. It states that the locus of a point equidistant from two given intersecting lines is the pair of bisectors of the angles formed by the given lines. Let the intersecting lines be AB and CD. Let line XOY be the bisector of angle BOD. Let P be a point on XOY such that PM is equal to PN, where PM and PN are the perpendiculars drawn from point P to lines AB and CD respectively. We have to prove that P lies on the bisector of angle BOD, meaning P lies on line XOY. Let's prove the theorem. Let the distance between P and lines AB and CD be d centimeters. This implies that the length of PM is equal to the length of PN is equal to d centimeters. Now, we have two cases. If d is equal to 0, then point P lies on line AB and CD. This means P and O coincide with each other. Hence we can say that P lies on the bisector of angle BOD. Now, let us consider the second case, where D is not equal to 0. In this case, let's consider two triangles PMO and PNO. We are given that PM is equal to PN. We are also given that angle PMO is equal to angle PNO is equal to 90 degrees. Here OP is the common side of triangle PMO and PNO. Therefore, by the right-hand side congruency property, triangle PMO is congruent to triangle PNO. So by corresponding parts of congruent triangles, angle POM is equal to angle PON, as the corresponding parts of congruent triangles are equal. This implies that OP bisects angle BOD, or point P lies on the bisector of angle BOD. Hence the locus of a point equidistant from intersecting lines is the bisector of the angle made by them. The converse of the angular bisector theorem is also true. It states that every point on the bisector of one of the angles formed by two intersecting lines is equidistant from the lines. We are given two lines, AB and CD, intersecting at a point O, forming angles AOC, BOC, BOD, and AOD. We are also given that XOX' and YOY' are the lines bisecting these angles. Let L be a point on XOX'. Also, let LM be perpendicular on AB and LN be perpendicular on CD. We have to prove that LM is equal to LN. Let's consider the case when L coincides with O. Then it is equidistant from AB and CD. Now, consider the other case, when L does not coincide with O. Then L lies on OX. In right-angled triangles OLM and OLN, we have OL as the common base. We are given that angle LOM is equal to angle LON. Also, angle OML is equal to angle ONL is equal to 90 degrees. Therefore, by the AAS criterion of congruence, triangle OLM is congruent to triangle OLN. As we know that the corresponding parts of congruent triangles are equal, therefore LM is equal to LN. Similarly, we can prove the result when L lies on OX', OY, and OY'. Hence proved.